Hello, this is Caroline Marciano, and this is Machine Learning and Mario Kart Stream Analyzer, written and recorded by Caroline Marciano, charts and size by Caroline Marciano, unless otherwise stated, illustration by Cara Viro, neural network terminology reviewed by M. Ratsim, author of Raymancer, a NIM implementation of n-dimensional tensors with some neural network implementations as well. It's basically a NIM version of PyTorch. So here's the appendix. This presentation is split into 5 separate parts. So part 1 is prologue, part 2 is background. We're going to be talking the basics of machine learning. In order to know how MKSA works, you need to know about neural networks and genetic algorithms. Part 3, MKSA. Part 4, reflection. And part 5, epilogue. So here's a visual language key for the flowcharts in this presentation. So from the top left to the bottom, to the right to the bottom, a cube is a function code, that's a decision branch, end, start of new loop, like that's where everything begins or ends. It signifies something continuing or something ending. It's the end point or the start of something else. The rectangle is a group of data. Internally, it's not created externally, and the rhombus is a member of said group. The rectangle with 2 lines is outside data, a parameter, or noise. In the modern developer ecosystem, machine learning is thought of as a strict subset with actual meaning. Almost always, it's associated with Google, Microsoft, and OpenAI's competing products. These are massive, astonishing projects of data amassed and calculated by a supercomputer, and thus is basically impossible for small firms to be able to reproduce. This is also a relatively recent phenomena. We haven't been able to run these things at scale until relatively recently. This is important because machine learning is not a new phenomena. It's been theorized and implemented since basically the dawn of computing. So when we talk about it as only a strict, narrow subset of its actual meaning, we're losing a lot of the built-up knowledge and tools we've acquired over a long time. Machine learning in its most simple form is the process of a program adapting to perform a task without specific engineered intent. It learns usually from data and generates models, which can be applied to general data, such as a program which can identify a Chinese character from a vector graphic of poorly drawn Chinese characters, but with an actual name of the character attached to it. It can look for similar data, compare it to what it knows, and try to guess the character. This is powerful and is opposed to procedural programming, wherein a procedural program is designed from start to end procedurally to follow a process that is reproducible and deterministic. So if A, then B, then C, then D. Machine learning doesn't necessarily do this, and maybe you don't have fine control over the process as you would in a procedural program. Because while models can be deterministic, they are not procedurally designed. They are only a product of the procedures that parse the data that make it up, and so they are a product of both the quality of the procedures that parse the data and the data itself. Briefly, there are methods of action of machine learning implementation. Common ones are classifications. From a set of defined potential classes, it determines which one it is. Regression. From existing data, predicting trends in future data. Generative. Generating new data to fit a certain task or parameters. Optimization. Finding the optimal parameters for a given function. These are not all, but the most common. These can be chained and combined to create models for things such as language modeling, generating, parsing, correcting, predicting, computer vision, seeing, be it the world around you in a Tesla, or static rank numbers in Mario Kart. MKSA uses classification to achieve computer vision. Note, these are independent from the different types of machine learning. The different types implement these mechanisms in order to achieve their goals. So basically, you use machine learning to achieve classification, regression, generative, and optimization. These aren't the types. Like, you can do any of these with a neural network, or a purpose-made system, or, as we're going to talk about later, a genetic algorithm. Now, it's important to note that machine learning begets machine learning. Because of the distinctive discrete types of machine learning, it would be remiss to mention its proliferation effects and tool chains. Machine learning can metastasize across your tool chain. It can spread and colonize other parts because it can be advantageous to train a classification model and then compete it against a generative model to create new data which fits the prior classifications. so you can fake data for whatever purpose you need. For example, if you make a model which is really good at separating human-made text and non-human-made text, and you incorporate that into your English text generator, you can use that in the loss function to train your model to create text which cannot easily be identified as non-human by the classification. And this can be useful for a bunch of different purposes, and it's been extensively seen in production. Neural networks are inspired by nature, principally information propagation through human neurons. A traditional neural network is made up of 3 sets of unique neurons: intake nodes, hidden layers, and exit nodes. Intake nodes transform data, making it fit for hidden layers, after which the hidden layers actually transform the data, and the output nodes collect the data from the hidden layers and give you one output in the format you want, usually a float value. Each neuron in every layer is connected to every neuron of the next layer, but not each other, and it only goes forward. Each neuron's connection to each other is variable in strength, and this strength is determined by the optimizer, and it's called a weight, or weighting. When data is passed or propagated from neuron to neuron, it is transformed mathematically via functions depending on the neuron's network and circumstance. The transformation is governed by the neuron's unique mathematical value, and the amount of this mutation is directly determined by the weight of the connection. So every neuron transforms all data going through it, but the amount of transformation is the weight, and so every neuron changes the output of the neural network by varying degrees, and not representative of a total whole, so it's not proportionate. Some connections may do almost nothing to the output, but other ones may have extremely high weightings and change the entire output when it passes through the neurons because they have a very high weight. Learning is done by an optimizer and a loss function. A loss function judges the output for a given input from the neural network, and is fed into the optimizer. The optimizer takes this value and judges it over time and changes how the neural network is formatted, its weighting, its values, etc. I didn't mention this in the actual presentation, but neural networks have hidden layers, and they are called hidden layers because they are unknowable. You can't really understand them outside of the context of the neural network, and so most neural networks are black boxes, and you can't really figure out how they work. You can only witness what goes in and what goes out. This is a major limitation of neural networks. This is also true for genetic algorithms, which we'll learn about in a second. So this is an illustration by Carlo Virro, a great friend of mine. So every circle represents a neuron, and every line represents a connection between them called a parameter. And this doesn't actually illustrate the weighting, but maybe imagine a stronger weighting being wider and a less strong weighting being more narrow. You could see that each neuron is connected only horizontally, not vertically. They connect between layers, not between neurons. So here is an optimizer called ADAM, Adaptive Moment Estimation. We're only going to be covering the first 3 variables, because the last one is pretty self-explanatory. So the first variable is alpha, the step size, how often this optimizer is called. Next 2 are beta 1 and beta 2, the decay rate for momentum. The typical value is 0.9, as we want to have high weighting for the most recent gradients. Beta 2, decay rate for squared gradients. The typical value is 0.0999. This is because 0999 captures long-term memory of gradients. We want a stable estimate of variance. ADAM works by estimating the current learning rate and adjusting propagation according to its parameters. Each connection between neurons is called a parameter as well, but this is separate from ADAM's parameters. Keep those separate. For every iteration of the network, the loss function of each parameter is stored in an array, and at every step, alpha's value, a curve of change over time is calculated. This is a gradient. This is used to judge which connections are improving and which are not. If the parameters are determined to be important, their loss function is squared. Then this parameter's weights are compensated for, making them the most impactful connections within the neural network. So let's break this down a little bit. So a gradient is just a bunch of loss functions calculated into a slope. So you have, say, a step size of 20. For every parameter, there will be 20 different values to calculate a slope for. And from this, we can determine which ones are learning more. So since the loss function grades a parameter, we use this to determine its improvement over time. So if over time, over this step 20, we see that the slope is positive, that over this period it's improved, we will improve its weighting, otherwise we will make it worse according to the decay value. So if it's decaying, if it's neutral or negative, it'll decay according to beta 1 or beta 2, depending if it's squared or not. Atom decays weights according to their gradients, as well as their age, see beta 1 and beta 2. If a parameter stagnates, it'll fade away, leaving only important parameters. This leaves room for new parameters, well not new parameters, but new neurons to be formed to take their place, and for new parameters to be gauged between existing ones, so new gradients can be formed, and useless old junky data can be replaced with beneficial new productive data. It is important that beta 2 is a higher value than beta 1, because not only are squared gradients usually more important, so you don't want to lose them as quickly, but the weights can decrease exponentially more quickly as they are squared, versus not squared. I contacted Amaratsim for this specific segment as he wrote the atom for Arraymancer, and also thank you for the built-in article for describing the parameters for atom on the left here. I didn't write that. In the same vein as neural networks, genetic algorithms too are inspired by nature, particularly Darwinian evolution. They have the same mechanism of a loss function, except rather than mutating weights and mathematical operations, they use randomness and sometimes intergenerational breeding to achieve fitness. They are most appropriate in situations calling for optimization of a set of variables, as they operate directly on the variables. A generation is made up of a set of organisms, and after all of their fitnesses are calculated by a loss function, a percentile are culled. The surviving members then reproduce to make up for the lost organisms. Breeding can be done via mutations to the variables using noise, for example, plus or minus 0.5%. Alternatively, another way is to break down the learning process into chromosomal pairs, distinct set of variables, which are combined from all surviving members randomly and then mutated. The new organisms compete against their parents to replace them, as usually organisms are immortal. Gradually, each organism's parameters tend to plateau and not change that much, as the new generation is very unlikely to out-compete their parents. This would be similar to a flat gradient in a neural network. The organisms can be said to be most fit at this state, and the process comes to an end. So here is a flowchart made of a simple genetic algorithm. Starting from the top left, generation of N has their fitness evaluated for each member. If the member is not above a certain percentile of fitness for the generation, they are culled, otherwise they survive, and then they get on to reproduce and mutate and compete against their parents. In the software engineering space, there's a common axiom: garbage in, garbage out. This is never more true anywhere else than in machine learning. Data can only be interpreted by procedural systems when constrained. And remember, although machine learning models are not procedurally designed, they are still created by procedural systems, and they are still running on computers, so they are still procedural, so they still need constructive data. Otherwise, it's noise, or garbage. Data perfectly fitting constraints can be defined as quality. When creating these systems, we must ensure that all of the data we train it on is of value and importance to the topic at hand. No machine learning algorithm can function if data fed into it is incomplete, malformed, operated on incorrectly, serialized or deserialized in unpredictable ways, has too much noise, or is mislabeled. Under any of these circumstances, no machine learning can be done by any algorithm in the world. I cannot stress enough how important garbage in and garbage out is to machine learning. Mario Kart is a game franchise released by Nintendo, where players compete for first place. Players are graded on a scale of 1 to 12 depending on their position to other players, e.g. first place, second place, third place. The most recent game in this franchise is Mario Kart 8 Deluxe, Mario Kart 8 Stream Analyzer (MKSA) is a program written in Python for archiving Mario Kart 8 Deluxe games and tracking player performance over the course of a race. It implements a purpose-made machine learning algorithm for computer vision, namely static image detection. Its purpose is to, for every frame of a game, identify the player's current rank position. The data used to generate a player's rank over time is gathered directly from game footage. It is processed by cropping, increasing contrast, and converting it to a binary image, where each pixel is either on or off. This process is very important to computer vision and is referred to as edge detection. It allows for simple binary logic to process data, not needing to account for colors. It's worth noting that removing potential data points increases processing speed, but removes data points, so there's less information, so you might be losing something very important. Remember the axiom garbage in, garbage out? The models are generated from the same constraint in which the footage is processed for analysis. One model for a given rank 1 through 12. The models are generated per pixels, and thus can only work for the processing which they are generated for. Each model is generated from an array of static images of the same size. If the pixel is on in all images, it is added to the output before being serialized. A checksum for the arrays are created to prevent duplication, and then the model is added to the database if the checksum does not match any other checksum in the models. And then you can generate data using that model. This means that MKSA models are subtractive. The only way a pixel is added to the array of pixels checked for a given rank is if it's on in all images. The more images you add, the smaller that array is, as there's a less likely chance that the given pixel is on in all images. So, here is a processing example. On the left here we have a raw picture from the game, only cropped. And then we have the computer vision processed. That makes it easiest for computer vision to see. As you can see, it has only black or white in it. It's a binary. It's either on or off. There's no grays. And we see on the right the ML model for a 5. And we'll see that there is less ones in the ML model than there is in the black picture. That's because it's just an example that the models are subtractive. There's going to be less reliable information. See those like white lines for the TH? Those are there in a lot of images, but not all of them. So the model doesn't actually look at those pictures. The only ones that are a 1 in the ML model are the ones that it knows every image in its dataset is on. So here's the output. It's very simple, just a stair graph. It goes up and then it goes down. As you can see, this player started on a 9, and then they went up to 12, and then they went all the way down to 1, and then they went back up. RIP, you could have got 1, but I guess not. But there's a catch. If you look at this, unfortunately, ranks in Mario Kart 8 aren't actually fully static. They have an animation where they fall away and they reappear. And in between our islands of models, we only have noise. So the only way we could account for this logically is if we did one of two things. We make some kind of ML which is not static, it has an animation and it detects the fade in and fade out animations, or we just detect when the data is too noisy for us to make a good decision, and we just do something, we interpolate. So here's what this slide explains here. There's a big catch, and it also explains that the highest rendering layer is not used for ranks. Some things are rendered higher than the HUD. Another issue is that game capture mediums like capture cards are not perfect at resampling digital signals usually, and there's some noise in the video, but it's not a problem for end users, only computers looking at the footage and doing per pixel color analysis, so we need to catch up. So you have another illustration here by Caraviro, and basically, you see on the left here, we have the 7 for 34 frames, complete nonsense for 24 frames, and 6 for 10 frames. And we have the graph on the right, which is the actual output. It smooths it out so you don't see the noise, and you don't see random numbers in there. You just see a 7 or a 6. Here is a less simple graph, and it looks a little bit overwhelming, but I promise you it's simple. So, the red lines going vertically represent a interpolated value, and the green lines represent a consistent value. And between them, it's where it reads the number. So you see at the start, it only reads 9 after, say, 150 frames, but before that, it reads nothing. So then the 9 is pushed backwards, and then the 9 is pushed forwards until you get to the 11, which is unknown. So it reads red, and then it reads green, and then it reads red, and then it goes up to 12, etc. So you could just see here that between all the values, pretty much it almost always reads red, which, whatever, but the graph makes sense, and it appears to be correct. I checked this graph manually. Ideally, the less interpolation, the better. And the earlier we detect the ranks, also the better, because that's the more accurate the output is. It's how early we detect the number. So the charts in the red boxes represent the functions in the unboxed in thing up here. So our unclassified images go into our model generator, and then this gets a set, for the set of rank images, we get every single pixel in them, and if all the pixels are white, we add it to an array as the output. So basically, for one, we'll have an array of all pixels which are white in all of the images. So in order to classify an image, we get the image and we get our rank models. And since our rank models are really just an array of pixel positions, we query all of the pixel positions in the image. And we're only looking for on pixels. And so we count the number of off pixels. So basically, we get a table of the number of the rank to the number of black pixels, and then we add it to our error correction algorithm. So if the image isn't all black or all white, if the output of incorrect pixels for the given rank is less than 40, if the most likely rank, sorry, not the given rank, the most likely rank, and if the correct number of pixels in the most likely rank is at least 20 more than the second most likely, then we add it. So if the most likely has 0, and the second most likely has 20, we don't add it. It has to be 21. And then it's added to the output. So this is a bar graph, a very simple one. So we have an example of the output. So 1 equals 194, 2 equals 518, 3 equals 337, 4 equals 13. 1's a very big outlier here, and I put in the bar graph to show how much of an outlier it is. So the red is the number of total pixels in the rank, so we see that 4 doesn't have a maximum of 13 pixels. No, it has an average number, and so it being lower is pretty significant. So this is a full detail graph. On the y-axis we have the percentage of total pixels incorrect, and on the x-axis we have the number of frames. The above graph shows how we are reading it, and if there is no blue line, that means it's interpolated. And that's not necessarily a bad thing, but we want it to be as covered by blue as much as possible. We want it to be reading the number as consistently as we can. For example, you see after 2000, there's a 1, very likely a 1, that was only read for like a single frame and is interpolated, and that's still correct, but we want it to be as blue as possible. All procedural code needs to be designed to work in a set of circumstances, and it's input limited. It can be tested, every single circumstance edge case can be identified. However, for machine learning, edge cases can be hard to identify. As mentioned before, the quality is a function of the data it's based off and the functions which make up its body. Functions can easily be tested, but datasets less so. In order to find what your dataset or models are bad at, a lot of debugging time and searching for edge cases sometimes has to be done. One of your greatest tools for this is the previously used graph. As for all scientific endeavors, understanding and viewing data is crucial to essential operations. Additionally, versioning of models and the ability to recompile data is crucial, so you can A/B test. Changes in data can present butterfly effects, which you can identify once directly compared. However, large models created by neural networks, in particular, large production ones like ChatGPT, make version controls hard. They may be backed up once a month with no information between those two dates, or require extensive data logging to recreate the state of the neural network at a given point. In addition to the hidden layers and a knowable nature about their inner workings. This is the same race as previously shown, but the blue line is even less fit. And here is the tools I use to, allow for recompiling of data. So we have a compile event which takes in a unique combination of the race ID and model ID, which is then used to create a race event. The only way you can create a unique race event is with a, with the compile event, right? So this allows for non-duplicate race event data. And on the right, we have a deserialization of the video data, which is compressed in LCV4, and then it allows you to completely recompile it and get an A/B test. And then here is just an example of using that code. So it just queries the database using Python's SQLite binder, and then here's the output data. I worked really hard to get the dataset to be even more fit, and then you can see my work paid off, and you get a really interesting new data stream, which is way more fit than the previous one. So that's basically everything on how MKSA works. So now we're on why. Why respect purpose-made machine learning when neural networks can do anything they can? There's a reason that neural networks are a recent phenomenon. Neural networks learn extremely deeply and are capable of extremely complex pattern recognition and retention. However, they require an extreme amount of information to recognize these trends. Some ranks in the MKSA dataset have less than 300 samples, and the full size of the dataset is around 35 megabytes while uncompressed. Additionally, it requires so little CPU resources, it can run in the most basic Google Colabs, while being almost completely implemented in Python, relying only on the CPP-implemented NumPy. I wouldn't be able to make such a claim if I relied on PyTorch, which would double the resources regardless of it being implemented in CPP or not. The models a serialized neural network creates tend to be very large in size and need to be read into RAM or VRAM, creating additional system requirements. And large continuous learning models can not easily be versioned in the same way MKSA models can, because MKSA models are really just an array of, X, Y. That's all they are. Machine learning is not new, and we shouldn't confine our tools to a limited set of them. There's another answer to why, a more honest one. I could likely have achieved a much higher accuracy if I got a ton of information from Mario Kart, and then I categorized it and fed it into a neural network, wrote some unit tests and a loss function, and that would have maybe worked really well. But that wouldn't have made a good example of machine learning or a good presentation. What this project was actually intended to show was, without the barrier of hidden layers, a direct application of machine learning to data, a direct explanation and example of a computer learning to achieve a task via an observable and understandable mechanism, a medium to teach and educate myself as well as others, to unleash the digital power of a computer's most simple of operations, a binary comparison. To give an example to the fundamental immortal principles of digital logic, which our computers rely upon, how this can be applied to a task as an alternative to the mainstream conception of very abstract tools. Pick what best suits the project. Now, with everything said, if it wasn't clear enough, you can't design your own machine learning algorithm for every single case. Some problems have already been solved, or are way too abstract to make your own mechanisms. For abstract problems with abstract data, they require an abstract function and abstract tools. Human language cannot easily be distilled into binary logic. Its complexities and nuances and vastness require a breadth of data and dedicated tools to tackle. Hence, large language models dominate the spaces where abstract understandings of human language is fit. LLMs are neural networks trained on extremely, absurdly large datasets to understand human language to a practical level. AI image generation powered by human language prompts are built off LLMs principally due to the limitations of understanding human language. A general-purpose neural network cannot understand human language without extensive training first, let alone something as simple as machine learning and MKSA. Okay, so with everything over, thank you for watching. Here is the original writings. I wrote this while my computer wasn't working, so I wrote it all with my dip ink pens. They look insane because my handwriting is very poor. But thank you for watching. Here's the link to the Google Colabs and everything if you wanna check it out. I'll put a link for it in whatever place if you're looking this on LinkedIn or YouTube. Thank you for watching again.